Start the recording. Hello, everyone. Happy New Year and welcome back to High Energy Astrophysics Division seminars. For today, we have two talks. Both speakers are from CFA. So we are happy to start with our own people. I'm going directly to introduce the first speaker. He's Erwin Lau. He's currently visiting scientist at Smithsonian Astrophysical Observatory. He got his PhD at the University of Chicago, and afterward he spent some time doing research at the Shanghai Astronomical Observatory, at Yale University, and at the University of Miami. Just as a reminder, you can ask your question in the chat, and we'll read them at the end of the talk, but you don't need to wait for the end of the talk to post your questions. So, Erwin, if you can please upload. Yeah.
Yeah. Do you see my screen?
Yes.
Okay. Good.
Okay.
Thanks, Federico, for the introduction, and thanks to the organizers for giving me the opportunity to talk about my recent research. So I'm going to talk about modeling galaxy clusters with Baryon Pasting for future multi-wavelength cluster surveys. And these are works that I've been collaborating with a bunch of people, including Akosh at CFA, Daisuke and Guy at Yale, Nico Capilouti at Miami, and also Miller has been very helpful, and also other people at other institutions. So I'll just get started. I've been interested in galaxy clusters for a while now, and the aspect that's most interesting to me is that, well, galaxy clusters, they are very good probes of cosmology, as well as astrophysics. So, this is a statement from the Cosmic Visions 2016 report from the Department of Energy, saying that the number of massive galaxy clusters would emerge as the most powerful cosmological probes, provided that if we can measure the mass of clusters very accurately. And to do that, we have to understand cluster astrophysics very well. So this has been a challenge for the upcoming surveys in X-ray from Evo-Theta, in the microwave through the Sun-Yuzadovich effects with Simon's Observatory and CMB-S4, and other optical probes like the Rubin Observatory and DESI. So to understand cluster astrophysics and how that would affect the way that we measure and estimate mass in clusters, the traditional method is to look into cosmological simulations, where in these simulations we basically follow the formation and evolution of galaxy clusters and the gas physics. And because the formation of galaxy clusters and all the gas physics, they are very nonlinear. So numerical simulations has been the method of choice for the past decades or so to study the impact of astrophysics on how we measure cluster properties. But in the era of very large-scale surveys, just having numerical simulations is not enough. So the main scientific goals of these multi-wavelength scientific surveys, multi-wavelength galaxy surveys, is to basically maximize the scientific returns for the expected large number of clusters and groups that we expected to detect in these surveys. And this will be, so the main challenge would be to connect the gas physics in these halos and these observed halos with the dark matter halo underlying dark matter halo properties that allow us to constrain cosmology. And this would be very difficult with the traditional large-scale cosmological simulations, because even with the largest simulations to date, it's still very difficult to probe the cosmological volume that will be measured in these upcoming large-scale surveys. So our solution is to develop and provide another way to model cluster astrophysics, which we call Baryon Pasting. Basically, it constitutes a very simple and physically motivated, as well as computationally efficient way of modeling various properties of gas physics in galaxy clusters and the cosmic web. And the core engine, what we call Baryon Pasting, is the gas in hydrostatic equilibrium in dark matter halo potential, with an addition of a number of physics modules that sort of realistically model the astrophysics of in galaxy clusters, and that includes cooling and star formation, gas heating by supernova and AGN from feedback, cool core modeling, bulk and turbulence gas motions that are generated from mergers and accretion, as well as gas density clumping in the outskirts of clusters, as well as the triaxial shapes of dark matter and gas. So we calibrate our gas model in the Baryon Pasting code with some of the recent X-ray observations. So shown here, it's the comparison of our gas model and density profile, and as well as the M-gas M relations. So we calibrate the gas density profile with the recent measurements of the Chandra SPT cluster samples from McDonald et al. And we also compare our predictions of the gas mass, total mass relations from group scales to cluster scales with a bunch of X-ray observations from Chandra and XMM. And in general, we are confident that our gas model described the these X-ray observations very well. So we calibrated parameters, gas astrophysics parameters with these observations, and we are able to, in position of making some predictions for the large-scale surveys. And to do so, we take a halo light cone, basically just light cone simulations with halo mass and redshifts and the position on the sky. And we use our Baryon Pasting model to paste X-ray surface brightness profile and also the Compton-Y profile onto these dark matter halo and produced large-scale maps. So shown here, we apply the Baryon Pasting model onto the Cosmo DC2 dark matter halo light cone, which is a 440 square degree sky area. So shown here, it's the dark matter surface density map on the left panel, and we show the corresponding X-ray surface brightness maps and the thermal SE maps in the middle and the right panels. So with these maps, we're going to explore the impact of astrophysics in the X-ray and SE observables by varying the parameters in our gas model. So one of the main observables that we can measure in these large-scale maps is the angular power spectrum. Basically, we measure the clustering power of the cluster and groups as a function of the angular separation of the clusters and groups, and this will measuring the power spectrum of these cluster and groups will give us constraints on cosmological parameters like sigma 8, which is the amplitude of the amplitude of the metapower spectrum, as well as the omega matter, the matter energy density of the underlying universe. But the power spectrum itself in X-ray, they are also sensitive to the cluster astrophysics, and this is demonstrated in the plots here. So we generate a bunch of maps with different degree of astrophysics. In particular, we look into the two major uncertain astrophysics in galaxy clusters, namely turbulence generated by mergers and accretion, as well as feedback from supernova and AGN. And if we increase the amount of turbulence in our model, we find that the amplitude of the power spectrum are suppressed. And physically, that's because if you have more turbulence, you're decreasing the amount of gas with high enough temperature to emit an X-ray. So that generally suppress the amount of clustering power across the board, across the angular scale in the power spectrum. And similarly, if you have increased the amount of feedback energy that's input to the into the intracluster gas, you are going to decrease the amount of gas emitting in X-ray. So in a way that, in the same way, you're suppressing the amount of X-ray emission of the halos. And these effects can be seen in the Baryon Pasting maps, X-ray surface brightness map produced by Baryon Pasting that is shown on the left-hand side, which we show the maps with low amount of turbulence, high amount of turbulence, low amount of feedback, high amount of feedback. And you can see that if we dial up the amount of turbulence and feedback, you're generally suppressing the amount of X-ray emissions in the maps. So this demonstrated that the X-ray power spectrum is sensitive to the cluster astrophysics, and particular non-thermal pressure, which also another name for the turbulence, and feedback from supernova and AGN. And this turns out to be the key if we are going to constrain cosmological parameters in future multi-wavelength surveys. And this is results from our earlier paper where we predict that if we combine X-ray, optical, and also microwave maps together and do a cross-correlation study, we are able to constrain cosmology and astrophysics, cosmology and in particular W0, the equation of state of dark energy, as well as some constraint on the H0. But the key here is that with X-ray, by adding X-ray measurements we are able to further improve the constraints on these cosmological parameters because with X-ray we're able to improve the constraints by minimizing the degeneracies between these astrophysical effects like turbulence and feedback with the cosmological parameters that we like to constrain. So as a demonstration of how we are going to constrain astrophysical effects and cosmology with X-ray power spectrum, the first thing that we try to do is to look into how our Baryon Pasting model are able to interpret the EFETS X-ray power spectrum. So the EFETS, which stands for the Evo-Theta Final Equatorial Depth Surveys, which I think Amelia will talk about in depth in her talk later on. So it's a 104 square degree survey, which is, you can say that it's the largest continuous area sky survey to date, except ROSAT, which is like already 30 years ago with very low sensitivity. So we use the EFETs, and we measure the power spectrum of EFETs and trying to interpret with our Baryon Pasting model by comparing the model power spectrum predict model and compare with the measurements. And we find that our model provides a reasonable agreement with the EFETs power spectrum. That's also including a where we also include a additional component that describe the unresolved point sources in the measurements. However, because of the limited sky area of the EFETS field, it's limited by cosmic variance, and we are not able to derive strong constraints on both cosmology and astrophysics. However, with the upcoming full sky Evo-Theta data, which will come out at the end of this year, hopefully, we're able to make better constraints on both astrophysics and cosmology due to the much larger sky area available in the ERAS survey. So we use the Baryon Pasting to make Fisher forecast of the cosmological and astrophysical constraints, and we find that with the Evo-Theta, even with the year one data, we are going to get very good constraints, marginalized 1 sigma constraints on both omega matter and sigma 8 to the 3% level, which are competitive to other cosmological probes. So another thing that we can use baryon pasting to look into is the amount of scatter in the mass observable cluster scaling relations. And one of the overlooked effects in galaxy cluster observables, in particular in mass scaling relations, is the fact that galaxy clusters, they are not spherical, which is evident seen in observations as well as numerous cosmological simulations. And here I'm showing a example of clusters not being spherical from the mock triangle maps of the Omega 500 cosmological simulations, where we show 2 clusters. One is a dynamically relaxed with a relatively quiescent mass accretion history cluster, which shown here appear to be much rounder and spherical in the X-ray morphology, as opposed to a recently merged fast accreting cluster, which shows a higher ellipticity along the axis of the merger. So that's basically show that the X-ray morphology is directly related to the dynamical state of the cluster, and that's not surprising. But the important thing is that this the dynamical state of the cluster, which is manifest in the X-ray morphology, especially in the aspherical shape of the cluster, it introduced a systematic trend in the scatter in the scaling relations. So here I'm showing again the temperature, X-ray temperature mass scaling relations from the same halos that we analyzed in the Omega 500 simulations, where we look at how the more spherical cluster and the less spherical cluster lies in this TXM relation. And more spherical clusters, because they are formed earlier, the gas are able to thermalize and equilibrate with the underlying cluster potential much earlier. So the gas temperature, they are much hotter than the less spherical and lately formed halos, which the gas are still in the process of thermalizing because of that. And that will introduce a systematic scatter in the TXM relation. Basically, for a given mass of halo, you expect that more spherical and early formed halo that have higher temperature than less spherical and recently formed halos. And we can forward that this model of cluster shapes and how and measure the impact of the cluster observables in the baryon pasting code. So by calibrating the cluster shapes from hydrodynamical summations, we can apply that in the baryon pasting model and paint the shapes of gas directly onto the large scale maps. So here I'm showing an example of the thermal SE maps with and without the implementation of halo asphericity. So this is the same region of the map, the same halo, one with aspherical halo, another with the spherical halo. Another important effects in that we also put into the baryon pasting model is the effect of miscentering. So miscentering between the gas center, say the X-ray peak, and the true center of the halo that is represented by the diameter density peak. And these offsets are usually due to effects of mergers, so which separate the gas center from the potential of the underlying diameter halo. And in the baryon pasting map, we also take into account of offset, which we have implemented a way to model the offsets from hydrodynamical summations. And here I'm also showing an example of a galaxy cluster halo with and without the effect of miscentering. So the red cross here is the true diameter halo center, and with the effect of miscentering, we are offsetting the gas distribution from the true diameter halo center. And by producing Baryon pasting maps with and without the effect of miscentering and triaxiality, we're able to basically compute the amount of scatter and bias introduced by a spherical halo shape and miscentering. So here I'm showing example of our results, showing that how the X-ray luminosity of the gas is affected by triaxiality, miscentering, and how it compares with the intrinsic scatter of the halo due to formation history of the halo and the baryon gas physics and core. So halo triaxiality or halo spherical shape, they introduced a scatter of around 4 to 5% in both the X-ray luminosity and also the Compton Y parameter. And with centering, we also see a similar amount of scatter at the group mass scales. So this exercise demonstrates that we can use the Baryon pasted maps to identify the amount of scatter, quantify and identify the amount of scatter generated by these physical effects at one at a time, and this is how it, and compare that with the with other sources of scatter. So at the interest of time, I'll stop here, and so in summary, I hope that I've demonstrated the way that Baryon pasting is a powerful tool for forward modeling astrophysics in upcoming multi-wavelength cluster surveys, and I look forward to apply the Baryon pasting map to the full sky EVO-CETA data in the coming year. So I'll take questions from here. Thanks.
Thank you so much, Erwin. Very interesting and promising method. I think I see clapping hands. Thank you. I think we had a question from Urmila, but I suspect that they were both questions were both addressed. If not, okay, I have a thumb up. Thank you. So, and then looking for hands raised, we have Anthony. Please go ahead.
So, what is the benefit of blank sky X-ray surveys? I would think that that you could get all the information there was to get by surveying in the Sunyaev-Zeldovich effect, finding all the clusters that way, and then pointing a big X-ray telescope at the clusters that exist. So what's the additional advantage of area surveying with X-rays?
Yeah, the advantage of just surveying the whole sky and measuring basically the 2-point statistics and 1-point statistics from the full sky is that it also contains information that are not included in the resolved galaxy cluster. So in particular in SE surveys, for example, Planck, there's limited in angular resolution. So you're missing many of the group size halos and unresolved that are unresolved in these SE maps. And similar argument can go for the X-ray surveys. And so by looking at the angular power spectrum, for example, it contains extra signal from these unresolved halos that you typically won't be able to probe with the resolved cluster measurements. So I'll argue that it contains extra information than just the resolved halos.
Thank you, Erwin. Do we have more questions? Okay, I don't see any hand raised. I don't see anything in the chat. So thank you again, Erwin.
Thanks.
Okay, so let's move now to the second speaker, who is Urmila Chadayamuri. So she's currently postdoctoral fellow at the Chandra X-ray Center within the CFA. and she works on simulations of galaxies and large-scale structures to extract cosmology from multi-wavelength observations. Aside, she cares a lot about explaining science to non-academics and encouraging scientists to think about their impact on society. The title of the talk is The X-ray Atmosphere of Isolated Galaxies, a view from Zeta and implication for galaxy feedback models. Thank you, and I'll give you a 2 minutes warning as requested. Go ahead, please.
Thank you, Federico. And thank you